Hello everyone, welcome back to another OpenShift Commons. As you can see, I've changed my background and this is special for today because we are talking storage. Many of you don't know, but those that are here from Red Hat may have seen a lot of our storage discussions, and you spent a lot of time with me here in my dining room, so welcome back. And we are also changing it up today. Today, we have an upstream discussion. I'm always excited about those. It's so important that we work upstream with the CNCF, and today we have members from Tag Storage talking about a topic that is very important to pretty much all of us, especially enterprise installations and anybody that is concerned with how to get your data back or your applications back if something happens. So today we have Alex Cherkop from Storage OS. He is the CEO, but also he is the CNCF co-chair of Tag Storage, and Tag stands for Technical Advisory Group now. It has been changed from SIG. And also Raffalele Spazzoli, who is a tech lead for Tag Storage. So very excited to have you both. Thank you so much for joining us. And Raffalele and Alex, if you'd like to tell a little bit more about what you do, especially with Tag Storage, and then dive right in.
Absolutely.
Alex, you go first.
Thank you so much, Corinne, and so glad to be here with the OpenShift community. So the CNCF a couple of years back had created SIGs, and SIG storage, in fact, was one of the first SIGs that we created, and the purpose was to help the CNCF with evaluating projects and to create content and educate an educational material for the end users and the community. And since then, the SIG has been renamed to Tag, just because SIGs were getting confused with the Kubernetes SIGs. And you know, as Karina mentioned, Tag stands for Technical Advisory Group. So I'm the co-chair of the group together with Jing Yang and Quinton Houle, and we also have a number of tech leads, of which Raffalele is one of our newest members. So I'd like to pass the baton on to Raffalele to introduce himself too.
Thank you, Alex. Yes, I work at Red Hat as an architect in consulting, so I help customers build their cloud-native solutions, and recently joined the Tag Storage to work together on the topic that you see on the screen today, which is cloud-native disaster recovery. This is a work that I think started about a collaboration that started 9 months ago. I think it was fall of last year when we started talking about if this was a good idea or not to explore in this particular tag, right? Or it should belong somewhere else. And then we started sharing some ideas, and we are now creating a white paper that I think we're going to publish soon. And today we're going to present some of the results of this white paper.
Indeed. So this is particularly exciting for the Tag, because we've had a lot of demand and in fact a lot of feedback in the different Tag calls, which Raffalele has been very patient with, and also it's meant that we've been able to iterate on the document. And just for everybody's benefit, when we talk about storage in the CNCF and persistence, we're not just talking about a volume or a file system, but we cover kind of any type of persistence layer, including databases and object stores and key value stores, for example, as well as traditional volumes and file systems. And I think the key thing here, and keep me honest here, Raffalele, I think what we're trying to do is to make sure that developers and DevOps teams and SREs, etc., have the information and the tools and examples on how to adopt some of these different technologies in a cloud native way, because for the first time in a long time, it's no longer infrastructure teams that are making these decisions, but it's developers and their deployments and understanding the storage subsystems and the different technologies that are available with cloud native technologies is extremely exciting and enables so many new use cases, which Raffalele will cover shortly.
Yeah, that's exactly right. I totally agree. And what we would like to do today is to present an approach to disaster recovery that we call cloud native. Obviously, it focuses on stateful workloads, and that's the storage workload that Alex was mentioning, all of them, right? It turns out that the hard problem that you have to solve when you distribute a stateful workload are always the same, regardless of the kind of interface that you expose. So it doesn't really matter if you are exposing block storage and a block storage interface, or a message queuing, or a SQL database. The internal sync is really the hard problem that you need to solve, and that's what we explore with this white paper. But from a user perspective, the concept that we would like to make people aware is this new concept of cloud native disaster recovery. This is, we call it cloud native disaster recovery. I just said new concept, but the approach, it's something that you could have done even in the past. Our point is really that with cloud native approaches, it now becomes less complex and more easy to create these architectures and this deployment, and probably less expensive. And the way we define this cloud native disaster recovery is by contrasting it with traditional disaster recovery. We had an internal discussion in the tag whether calling this traditional disaster recovery was correct or not. By traditional disaster recovery, we mean what you normally would find in many enterprise customers. So not the big web scalers, not the newer startups, but the enterprise customer that many of us work with. So let's go down these columns and rows one by one. I'm going to try to keep it quick because we don't have a lot of time, but and create this contrast and talk about what cloud native DR is. Type of deployment. So are we deploying active-active or are we deploying active-passive? In most traditional DR scenarios, what we see is an active-passive deployment, especially for the stateful workload. You may have stateless workloads that are active-active, but they all point to a single active site, and then there is a passive site for the stateful part. That's often what you see. For cloud native DR, we are proposing that it should be active-active. And then obviously we're talking disaster. So there is a disaster situation. How do we detect it? With traditional DR, in most cases, it's a human decision. Somebody who says, okay, this is really a disaster. We need to trigger the disaster procedure, recovery procedure. It's a human decision. In cloud native DR, we want it to be autonomous. We want the system to realize something is going wrong and react to it. And then the recovery procedure itself, what we see is normally a mix of manual and automated tasks. Maybe the tasks are mostly automated, but somebody is triggering them in a manual way. That is, at least in my experience, what I see the most. In cloud native DR, we want full automation on the recovery. Whatever the stateful workload needs to do to reset itself or reorganize itself, and the replicas and the partition to continue servicing. And then, the two metrics of DR are RTO, the recovery time objective, which is how long the system is down and how soon we can get the service up and running, and recovery point objective, which is a measure of how much data is lost because of the disaster, and it can also be a measure of how much inconsistency I have created if I have multiple copies of the data, right? So for RTO, for traditional, we usually have we could have good enterprises that are close to zero, but normally we have hours to recover from a disaster. In cloud native DR, we want this to be close to zero. Essentially, a couple of health checks have to fail, and then we realize the situation is a disaster, and the system will start bringing the traffic to the healthy locations. And for RPO, again, you could have close from exactly 0 to, again, hours of loss. I usually see order of minutes to hours in terms of loss, data loss. In cloud native DR, you have two options here. You can do strongly consistent deployments, which will have exactly 0 data loss, and you can do eventually consistent deployments, which may have close to 0 data loss in normal circumstances, but you're not guaranteed in this situation that the data, once it's reconciled, is exactly correct, right? It's going to be consistent, but it may not be correct for your application. So that's a caveat of the eventually consistent systems. And then from an organizational perspective, what we notice is that in traditional enterprises, application teams are normally formally responsible for the business continuity plan of their service. But what they do is they turn around to the storage team and ask them, what are the RTO and RPO that you can guarantee for the storage that we use, and then they adopt that as their standard. So de facto, the storage team is the driver of the enterprise DR strategy. And when instead we are arguing here that with cloud native DR, it's going to be the application team that will have to choose a correct piece of middleware, a correct product to handle their state, right? And then they will use that product to organize the DR procedure around it. And then one other observation that came up working with this new technology is that DR for traditional enterprise, it's really the capability that you need to do disaster recovery and instantiate this procedure are coming normally from storage in the shape of maybe backup restore or volume replication, whether synchronous or asynchronous volume replication. Instead, for cloud native DR, we noticed that this capability are coming more from networking. And we see the need for east-west communication between your failure domains, so that could be your regions or it could be your data centers, so that this middleware that is this new generation middleware the instances can cluster up, can find each other and cluster up, and then we see the need of global load balancers in front of the regions or in front of the data centers, which we need a way to direct the traffic to the healthy locations. So it needs to be a smart, intelligent global load balancer. So hopefully we give you an idea here of the differences between what we call traditional and cloud native DR. Go ahead, Alex.
I was just going to say one of the key things here is what we're talking about, I think, and again, keep me honest here, Raffalele, is we in a cloud native world where applications are effectively composable and the infrastructure is declarative. What we're talking about is cloud native gives you a lot of the tools that are available to automate and to manage disaster recovery, just like any other healing process that would take place in a standard cloud native environment. And so, we kind of acknowledge the fact that this isn't necessarily straightforward. Some of these technologies are also fairly advanced, but the point is that the cloud native, these new cloud native architectures, and Raffalele will talk about a reference architecture with some of the options available, actually enable organizations to have automated failover and automated disaster recovery processes with better metrics in terms of RTO and RPO than you'd get with the obvious manual failovers and manual tasks that you'd have in a traditional system, which I think is extremely exciting, because what we're effectively saying is we've made applications composable, and developers can declare what their applications need from an environment, and now we're kind of taking it a step further and saying that also applies to the disaster recovery process.
Right, exactly, and it is exciting. I find it very exciting, and maybe some of you may doubt that it's even possible, right? Or may say, the story that I've been told many times is I can reach RTO and RPO as close as zero as I want, but the cost increases exponentially. We don't think that this is true anymore. It's actually a matter of composing the architecture in the right way, but the cost does not increase exponentially, and you can actually reach these numbers with a relatively inexpensive deployment. And I use the word relatively, but certainly not something that grows exponentially. And so, talking about how we can build these architectures, here we are showing a strongly consistent deployment where we have a stateful workload that is capable of handling this horizontal state sync in the proper way, guaranteeing that there are correct replicas in the correct regions or data centers. We need 3 failure domains. In this case, they're data centers, right? We need 3 of them because otherwise we wouldn't reach the quorum. And as I said, in front of the stateful workload, normally we have a front end, probably a stateless front end, and in front of it, we will have a global load balancer. Okay, so this is a very generic blueprint that you can then reuse in several situations. I failed to mention, obviously, the stateful workload will have storage that comes from the local data centers, but as you can see, we don't rely on storage capabilities to replicate across this data center. All the interaction is handled by the middleware, by the stateful workload. So how can we build these stateful workloads? Because obviously we are now relying more on the middleware, right? On the middleware side. I have a couple of slides to talk about this from a conceptual standpoint. I'm going to try to go fast here, so maybe we have time for exploring one of such deployments. So we need to define the concept of failure domain. Understanding the concept of failure domain, a failure domain is an area of our system that can go down or can fail due to a single event. So you could have nodes. Nodes could be failure domain, racks, clusters, network zones, availability zones, regions, data center. They're all failure domains, and if you look at them, they contain each other. You can scale out this failure domain from the smaller one, like a single server, for example, up to an entire data center. But the theory around this distributed stateful workload works the same regardless of the scale of your failure domain. Here in this conversation, we are talking about disaster recovery. So we are talking about failure domain being the data center, because that's what usually disaster means. I lose an entire data center, right? There is an event, and because of that event, I lose the entire data center. So we're talking about our failure domain of reference is the data center. And normally, so for disaster, we mean that we lose the entire failure domain, or in particular, the entire data center, if we don't specify what the domain is. And the disaster recovery is what happens when that happens, what is my strategy. High availability is slightly different concept. High availability is when within a failure domain, something breaks. Maybe I have one fault. What happens inside the failure domain? Does the service continue or not? And then we have the concept of consistency. That is the property of a distributable workload to all the instances observe the same state. Okay, so the state is consistent across the instances. We need that because when we lose a failure domain, we're probably going to lose some of these instances, and we need the state to have been synced everywhere so we don't lose it. Okay.
Yeah. And I think it's fine if you go into the next slide. On that point, the getting strong consistency is probably the single biggest architectural challenge, right? Trying to ensure you have strong consistency, which is one of those key attributes in any storage layer or database layer, etc., is effectively a balancing act between maximizing latency or even reducing latency and versus availability. And there's a very convenient cap theorem here, which is one of those things where you have three things. You have consistency, availability, and partitioning, and you need to pick two, basically. And I'll let I don't steal Raffalele's thunder, but I'll let him explain some of the details and how it applies to some of the different systems we're talking about.
Yeah. Thank you, Alex. Yeah, and yeah, you announced the theorem correctly, right? It's usually you pick two of these three: consistency, availability, and network partitioning. I should improve the picture here. I like to say the theorem is slightly differently, because I think it helps understand the kind of choices that are made in the software today, which is network partitioning is not something that you control, is a fault that happens. So a way of reasoning about the cap theorem is, assuming network partitioning, what do you want your software to do? Do you want it to be consistent, or do you want it to be available, right? Because you can only pick another one. The network partitioning is not something that you pick; it just happens. And that I'm showing in this little table here some of common software today that where the choice is very clear, right? If you choose consistency, you are it means you're building a strongly consistent system. If you choose availability, it means you're building an eventually consistent system. Both have pros and cons, right? They have their usages, but that's a very clear design choice that you have to make when you build software. And in reality, some of this system can even be tuned, and depending how you tune it, they can change the behavior from being available to being consistent. But they are all built around this cap theorem. There is a corollary to be kept in mind about the from the CAP theorem, which is the PACHELK, or PACHELK, I hope I pronounced it correctly, right? Which essentially it means, it says, in absence of a network partition, so when the network partition is not there, you can only optimize for latency or for consistency. So this is, I was recently doing some experiment, and it was very clear what the PACHELK corollary means. In particular, I was doing for Kafka, right? So if Kafka is one of those that is tunable. If you set Kafka to be consistent, and then you spread the cluster across highly regions that have high latency, you get a very, very high latency on the response for a single, communication, whether you're reading a message or actually producing a message. Reading is always easier. And that's just the nature of how this software works. That doesn't mean that, for example, with Kafka, you can't have still a significant amount of throughput, but each individual transaction will have a significant high latency because you have told Kafka you want to be consistent. Okay, so that's how this work, and this it's very nice. It's incredibly convenient to have a theorem to think about this thing because you can take a software that you don't understand, a piece of software you don't understand, and you can ask the vendor or whoever is the expert to talk about the software in light of the theorem and understand the choices that are made and that are made by that piece of software. And just that way you will understand a lot of how that piece of software behaves. Alex, were you about to say something?
I was just going to say, just for further information, we also have the tag has created a more generic storage landscape white paper, and in that we define all of the different attributes like availability and scalability and performance and durability, as well as consistency. And it's interesting to me because what we have here is different systems will have different use cases, and it's probably worth noting that no one system will handle all of the use cases because of course very high or very strong consistency also typically might have scalability or performance implications, and vice versa, for example.
Right. It's a trade-off that you have to decide for your product. So we said we have several instances of this software, right? Running and clustering up, creating a logical instance. How do they sync? We need consensus protocols. I'm going to go quicker in this slide, but there are two types of consensus protocol that I call share state and unshare state. Share state is to agree on a state that all of the instances need to have. For this kind of protocols, you can have a protocol based on a leader election. That is the one that accepts all the rights, and the other one are just followers, and the validated by the community, by the academy, the algorithm that have been validated by the academy are Paxos and Raft. In this space, Raft becoming more and more popular. So most of the software that we have mentioned so far, and we have even we have another list later, they're all based either around Paxos or Raft when it comes to synchronizing the same state. Then sometimes you have to synchronize different states, but you have to make sure that these instances have to agree on all writing or not persisting that state, right? For that, we have the well-known two-phase commit or three-phase commit protocols. Another thing to know about is, like I was saying at the beginning, the hardest problem that this stateful or storage software need to solve is really always the same, and that is I need to sync with the other peer, and then I need to persist that data. Somehow I need to have a consensus protocol, a list of operations that have happened, and then I have to store it to persist that information. you can. It's interesting. There is an interesting chapter in the SRE book from Google where they explain how to theoretically build a piece of software that can be reused across all of these stateful workload products, because at the core it's always the same. Naturally, if you do it that way, you wouldn't get optimized performance. So you have to. This is a theoretical approach. You have to still take your make your optimization out of it. But in reality, there are several companies, for example, that are using RocksDB, or there's another one from Apache, that there's a storage layer with some level of consensus protocol to coordinate instances. So if you put everything together, you need to have these reliably replicating machines, and then you can create partitions, so where you separate your data so that you can horizontally scale, and then you can create replicas where the partition is replicated in other instances, so you don't lose data when something goes down. And so if you look at this picture here on the right, this is the anatomy of a stateful application, at least a modern one, where you have two replicas here. Okay, each replica has several partitions, so we end up with 6 instances. Instance has its own storage, and then we have the coordination layer. Between the instances with the same replica, we use a shared state protocol, consensus protocol, because we are all storing the same state. And then if this particular software supports transactions whereby I do 2 operations on 2 different partitions, but I want them to be one logical transaction, then I will have to have an inter-partition coordination protocol, and for that I can use something like two-phase commit. So this gives you an idea of the anatomy of these stateful workloads that we can use to build what we call the cloud-native disaster recovery deployments.
I think just on that point, Raffalele, I think one of the exciting things here is that what is effectively happening is we're layering different proven technologies. So you might have sharding for performance, and you might have raft protocols for consistency, but you might also have a variety of different layers in that stack where for example you might have a SQL layer that's using a key value store, that's using a sharding process, that's using a file system, etc. And so it is really, more than ever before, it's kind of important to understand the different layers, because at the end of the day, the attributes of your system and your failover capabilities and your DR capabilities are going to be an amalgamation of all of those different attributes. Yeah,
I agree. I couldn't agree more, especially on the on those observation you made on the interface layer, what is called the API layer here. We see more and more products now that offer, for example, a SQL interface and then also a key value store. And it's clear what's happening, right? They are just adding a new API layer, but reusing everything that is below it. So it's relatively easy for them to do that. Maybe they don't always get all the optimization that they could possibly have, but it's easy to add additional functionalities to your stateful workload.
Yep, exactly.
Yeah. Here is just a table representing some of the workloads that we have analyzed and the choice that they make in terms of the replica consensus protocol, so the shared state consensus protocol, and the unshared state or shard consensus protocol. I would highly recommend, if you are considering a new stateful workload, ask your vendor or your experts what choices do they make in this space, because that already tells you a lot about the software that you're about to purchase. Some considerations around strong consistency versus eventual consistency, and they both can be approaches for cloud native DR, but they behave differently. For example, in terms of RPO, as we said, strong consistency is about consistencies, obviously. So we don't lose any data once we create a well-done deployment. So it's exactly zero, right? I had people they couldn't believe it, but it's exactly zero. I never lose data with this, assuming that only one disaster at a time happens. Okay, but you don't lose data. With eventual consistency, you may be losing, you may lose some data, theoretically unbounded amount of data, but in practicality, if the system is not overloaded, it's something close to zero, because it's just what was in the local cache that the system didn't have time to replicate. And another thing that instead you should consider is then when you lose one data center, one failure domain in an eventual consistent system, like I said before, the rest will keep serving. And so the two sides of this deployment may diverge in terms of state. And when they come up, they don't necessarily agree with the state. So there is a reconciliation, algorithm that will decide who is right. But this reconciliation algorithm may not reason the same way that your application from a business perspective reasons. So what I like to say is that eventual consistency does not mean eventual correctness in business logic terms. And eventual consistency may pose some additional design consideration to your developers. So I personally, if it is at all possible, I personally prefer to keep things simple for the developers and choose a strongly consistent deployment.
I think strongly consistent is the most predictable, and one of the points here about the minimum number of failure domains is that with strongly consistent systems, you effectively have an odd number of copies. Because you remember when we were talking about the cap theorem and we were talking about partitions, if a node is partitioned or is unavailable, effectively the remainder of the system still has a majority of copies of the data and can therefore make an automated decision as to who is up and who is down, and which systems are authoritative for that consistent system. Whereas in eventually consistent environments, it can be a little bit more complicated, because effectively some of those decisions can be delegated to the application, or some of those decisions could be delegated to reconciliation processes, which are not perfect. Hence, the reference to it doesn't mean eventual correctness.
Right. In terms of RTO, both will react in a few seconds, essentially depending on your health checks and the health checks that you set on the global load balancers, but also some internal health check that the system has. In terms of latency, strongly consistent workloads have a strong sensitivity to latency between these failure domains. That could be regions or data centers, and by and large, your latency will always be greater than the worst latency between regions that you have multiplied by 2, because it's always back and forth. So that sets your expectation, and that's to me that says not all the use cases. I cannot use strong consistency for all the use cases. I will have use cases that need really fast responses where I can't use this system. So I need to find different solutions. But if it's acceptable, if the latency that I have is acceptable, like I said, strong consistent keeps things predictable and simple for the developers. On the On the other side, eventual consistent instead is not affected by latency because essentially the system first writes locally and returns, and then it tries to synchronize with the rest of the instances. So that does not affect the client latency. That was a simplification, but it's a way to explain why they are not really affected by inter-failure domain latency. The throughput instead for both can scale linearly. As long as we have workloads that are touching all the partition, okay, so the requests are normally distributed and all the partitions are involved more or less in the same way. This system scale horizontally, scale linearly with the number of instances. So you want more throughput, just add more instances, increase the number of partitions, and you get the throughput that you want. And then, as Alex said, strong consistent as another constraint that some of our customers find taxing, which is you need 3 failure domains. In other words, if the failure domain is the data center, like we were saying, you need 3 data centers, and we perfectly know that some of our customers have, or some of the enterprises have 2 data centers, maybe in the same metro area. Okay, they would have very good latency between these data centers, but they don't have a 3rd one. So what can they do, right? At the same time, instead, eventually consistent workloads only require 2. Yeah, so there are solutions to get the 3rd data centers. One option is to go to the cloud, but that is certainly a constraint of strongly consistent system. We wanted also to share reference architectures for Kubernetes deployment. The first one that we shared was very generic. You can build it with VMs, but obviously we are looking at Kubernetes with special attention here. So not very different. We still rely on the stateful workload to do the horizontal sync. We still rely on persistent volumes provided by Kubernetes in this case, and then you will have some ingress and a global load balancer in front of it that decides where the traffic goes. So here, when we lose one side, essentially nothing happens. The global load balancer should realize it and just send the traffic to the other ones. Another thing that you should ask yourself when you build this architecture is, what happens if the clients can connect to my workloads, but there is a network partition between some of the data centers, and so one is isolated. For strong, consistent workloads, this is essentially equivalent to losing this data center, because all of these instances will become not active because they don't have quorum. And so the global load balancer should realize that this side is not responding and send all the traffic to the remaining 2. So the behavior should be exactly the same. We have also a reference architecture for eventual consistency, similar, right? Except you just need 2 failure domain or 2 data centers. Here the conversation is slightly different. When you lose, well, again, if you lose the entire data center, the global load balancer can only send you to the remaining one, and there is no real state divergence because there are no writes on the data centers that you have lost. Different story when you lose connectivity between the stateful workload, but the clients can still write, still have a way to write. In this case, you can have divergence of the state, and that's where, when we say, that's the conversation we were having before. This is a situation where at some point this fault will be corrected, the connectivity will be reestablished, the reconciliation algorithm will kick in, but the result that you get as the final reconciled state is not necessarily aligned with what you need in your application. Okay. We have some reference material here if you want to go a little bit deeper. This is our white paper and some blog posts around building this architecture in practice. And if we have time left, we can explore one of these environments together.
So if you think you can do it in 10 minutes, I'd love to. I think we all would love to see you go into a demo environment, but do you think 10 minutes is enough time?
It's going to just be an exploration of what we have, what I have. Or do we have, unless we have questions. If we have questions, I also would like to answer those questions.
Well, I have a quick question, just going from what you were talking about last. Obviously, one of the biggest considerations between strongly consistent and eventually consistent is the cost factor, right? So as you're working through this in tag storage, are you looking at TCO, or what do you, have you explored that in tag storage, the overall?
No, we don't focus on cost because we try to be product agnostic. So my only consideration is you have a third data center. That may mean more, that may be a significant cost depending on how you decide to implement that data center. If you go to the cloud, it's not actually necessarily a huge cost. It depends on how much you deploy, right? It's a pay-as-you-go model. But if you actually build a physical third data center, that it's a huge investment up front. The other consideration is some companies may be running on software that is not capable of being deployed this way. And so they may be facing a migration. Let's say you may have to migrate from MySQL to a new modern database that can actually be deployed the way I was describing. So, these migration projects can create some cost in an enterprise.
Yeah, I mean, I kind of knew the answer, but I was trying to tease out the, strong consistency is obviously the best choice, right? And then, all right, diving into your demo.
Keep asking questions. I'm going to describe this environment. So here, in the meantime, here I have three clusters. Okay, these represent my three region or data centers. They are in different, they are in Google and they are in different regions, as you can see, US East 4, US Central, and US West. Here, for example, I have one of these clusters. Obviously, I'm from Red Hat, so I'm using OpenShift because it's easy for me, but there's nothing in what we discussed that implies OpenShift. You can do everything with Kubernetes. So here I have Kafka deployed this way. You see 3 instances of Kafka, but this is the second cluster, 3 more instances. This is the third cluster, 3 more instances. These are all talking to each other. And I have, for example, here a Kafka console in which I can see that I really have if I go here, I have a 9-node Kafka cluster. You can see from the name of the instances of this node that I have cluster 3, cluster 1, cluster 2. So all of the cluster, OpenShift cluster, all of the instances that are distributed in different OpenShift clusters come together to create a single logical Kafka instance. If you notice this notation here, let me make it a little bit bigger. This is not the usual service name that you get inside of OpenShift. This is a new standard for intercluster discovery of services and endpoints. So it uses these cluster setups. uses this cluster set notation, and it also has the name of the cluster in which the pod is. And so these are actually the pods that we were seeing before. And I think I have a topic defined here. And if we look at this topic, look at the partition. It has 9 partitions, so it's well balanced on the cluster, on the available nodes of these clusters, and it has each of the. I configure Kafka to be strongly consistent, so each partition has 3 replicas, and each of these replica is in a different region. So if I lose a region, one of these will become red, but I still have 2 replicas, and I can still continue working. So that's how you can set up your workload. I also have in this experiment that I'm running, I also have a CockroachDB deployment. So CockroachDB gives you a UI where you can go and see what you have. So here it has this nice feature where you can see your cluster, how it distributes in a, on a map, right? So these are the 3 regions that I'm using from Google across North America. These are the nodes. Also in this case, I'm using 9 nodes, 3 in each regions, and then each node within the region is in a different AZ. So that I'm trying to get both local availability and global geographical availability. And we can see another nice feature of Cockroach that I like of Cockroach is, for example, that it calculates the latency between the instances and then uses this information to do some internal optimization. But as you can see, this is obviously a symmetric matrix, or mostly symmetric, and from west to east is where we have the highest latency, around 60 milliseconds. So that tells us, based on what I said before, that the best latency that we can get from a transaction here, once we have distributed the workload, the data across the 3 regions, the best latency is going to be around 120, something above 120 milliseconds. We get 120 milliseconds just from the network. Then there is, processing, writing, persisting, and all of that. So you can immediately start reasoning about, okay, what kind of workloads can I run on this database? So it's a trade-off. Yes, your workload may go a little bit slower than if it was deployed in a single region, but now you get that when you lose a region, you essentially don't have to do anything. The system will continue, the service will continue to be up, and the system will continue working. That's it. I think we don't have time to simulate a disaster and see how the system reacts. We would see that here, all of these systems, both Kafka and Cockroach, can auto-detect failures, and they will start reacting to it. We will see that we lose some nodes. We will see that some of the ranges, these are essentially the partitions, are getting moved around. And the system, like I said, readjusts to the new situation. Same thing does Kafka.
I think one of the key takeaways here is that we, in a cloud native world, we now have the capability of implementing disaster recovery with different storage systems and different databases and different tools. And in fact, you get an order of magnitude better automation and better flexibility than you do with your traditional systems. And I think this is sort of the next logical step for many enterprises as they adopt cloud native technologies and Kubernetes and OpenShift and cloud native storage solutions, as they look to migrate more mature workloads and more mission critical workloads that require disaster recovery. So my key takeaway here is understand the different layers in your system, understand the different attributes like the latency and the performance and consistency requirements of your applications, and then absolutely take advantage of the composability and the declarative nature of cloud native disaster recovery, and all the advantages that brings to your application, and touch wood, sleep better at night.
Thank you. And we had a question come in that I think we'll have to take to, if you came in from the LinkedIn event, longer than a minute, and it's a great question. What considerations are required for cloud native disaster recovery in a heterogeneous environment? If either one of you want to take it in 1 minute, otherwise we can push that to the LinkedIn chat.
Yeah, I'll try to answer quick. Go ahead, Alex.
No, go on.
Yeah, I assume by heterogeneous we mean that we don't have an homogeneous cloud provider or infrastructure underneath, right? Like I said, this architecture relies on capabilities in the networking space. So as long as we can do that east-west communication and we can discover the instances of our stateful workload on the remote domain, failure domain, and as long as we can set up some level of global load balancing, we will be able to create these architectures. And in fact, we are doing it. And what collaborating with some of these vendors, what we're noticing is how do you, in order to be predictable, in these deployments, you would like all of the instances to behave the same. But how do you, for example, provision the same IOPS across different cloud providers? They all give this capability or this SLA in a different way. Or how do you provision the same, computing power? They are slightly different. So those are the things that you may encounter, but there is no actually blocker to building these architectures across heterogeneous environments.
In fact, and I'll just take one more second here, I would kind of argue that tools like Kubernetes are actually designed to abstract your infrastructure and to give developers the capability of getting the same services from different systems. And I think the glue that holds that together then is the east-west networking and the load balancing services and things like that sit on top of that.
Thank you both for taking that last minute question. It's a very, very good one and very important. Thank you again. I will post the video recording and the slides at the LinkedIn group and then our LinkedIn event. And then we will see you all next time. Next Tuesday, we'll see if we have something scheduled, but see you all then. And thanks again, Alex and Raffalele. This is a great, important topic.
Thanks for having us.
Thanks for having us. Thanks, everyone.
Bye-bye.